Professor Dave and Chegg here. With some periodic trends covered, we are ready to find out what happens when two elements come into contact with one another. There are several options for how they may interact, meaning that there are different ways that chemical bonds can form. So let's go over these now.
When an element with a very high electron affinity, like chlorine, and an element with a very low ionization energy, like sodium, come into contact with one another, electron transfer will occur. One atom really wants to gain an electron, and the other has no problem losing one, so the electron is transferred from one to the other, generating two ions. In this case, we would get a sodium cation and a chloride anion. Notice that these each now have a noble gas electron configuration with an outermost shell that is completely full. This is a particularly stabilizing situation, which explains why these atoms will readily adopt these configurations. When cations and anions are near one another, they will interact via ionic bonds. These are strong electrostatic interactions that allow for the formation of ionic compounds, such as sodium chloride in this case, which we know of as table salt. Another way of looking at this is to examine electronegativities. If the difference in the electronegativities of two elements is sufficiently large, above 1.8 or so, electron transfer will occur, and we will get ions that then participate in ionic bonds. We will also want to understand some things about the strength of these ionic bonds, and this will involve defining lattice energy. Looking again at sodium chloride, this consists of sodium cations and chloride anions arranged in a grid, with the ions arranged in the geometry that will allow for the maximization of electrostatic interactions between oppositely charged particles. The stronger the interactions, the greater the lattice energy, or the energy that would be required to disrupt the lattice and separate all of the ions. There are two main factors that influence lattice energy. The first of these is the magnitude of the charge on the ions. So with sodium chloride, we have a +1 cation and a -1 anion. But ionic compounds can have cations or anions with charges of +or -2, +or -3, and so forth. The greater the magnitude of the charge, the stronger the attraction between the ions, and the greater the lattice energy. The second factor is the size of the ions. The electromagnetic force drops off as distance increases, so the closer the nuclei of the ions are to one another, the stronger the attraction. The smaller the ions are, the closer the nuclei can be to one another, so smaller ions correspond with a greater lattice energy. This can be observed by keeping the identity of one ion the same, but altering the identity of the counter ion, and observing the lattice energy changing according to size. So that covers the first type of chemical bond, but very frequently elements will not transfer electrons from one atom to another. Rather, they will share electrons to form covalent bonds. These can occur between atoms of the same element, like two hydrogen atoms, or between different elements that don't have such dramatic differences in electronegativity, such as carbon and hydrogen, that will share their valence electrons. To get a bit more technical, when a covalent bond occurs, such as with a molecule of H2, it is because the electron from one hydrogen atom feels the pull of the nucleus of the other atom, and vice versa. So it's as though each electron belongs to both atoms. In this diagram, we can see that as the hydrogen atoms approach one another, their 1s electrons begin to overlap, and an ideal internuclear distance is found. That is the distance between the two protons. There is a dip down in energy because if each electron is interacting with both protons, that is a stabilizing and therefore energetically favorable situation. However, if we push the protons too close together, it begins to become less favorable due to proton-proton repulsion, just like if we were to compress a spring, which is why we see the curve rise steeply to the left. It is this phenomenon that reveals the internuclear distance that contains the lowest potential energy and therefore the ideal covalent bond length between the hydrogen atoms. So we can now describe how a covalent bond forms, but we must understand that there are different types of covalent bonds, and a bond formed between two identical atoms will necessarily be different than one formed between two different types of atoms. Say that we are looking at a covalent bond that forms between two identical atoms, like the bond contained in a molecule of H2, or any other diatomic molecule of one element. In such a case, the electrons will be shared precisely evenly. The two atoms have precisely the same electronegativity, so there is no basis for one atom to hold on to more of the electron density than the other. We would call this a nonpolar covalent bond. If the two atoms participating in the covalent bond belong to different elements, like a molecule of HCl, it might be possible that the electrons are not shared evenly, but rather that the electron density is more attracted to one of the atoms than the other, which we can see is happening because the cloud of electron density is more prominent on the chlorine atom than the hydrogen atom, due to the fact that chlorine has a greater electronegativity. If the electrons are shared unevenly, this is called a polar covalent bond. In a polar covalent bond, the atom that is electron deficient is symbolized with a delta plus, and we will call it partially positive. The atom with the electron excess will be marked with a delta minus, and we will call it partially negative. These partial charges are not formal charges like we find on ions. They just represent the unequal distribution of the electron density in the bond. We can also mark this with a dipole arrow. Here, the arrow will point in the direction of the electron excess, with an additional line on the other end to resemble a plus charge, indicating the side with electron deficiency. So to summarize, when two elements interact, the electronegativities of the two atoms in the bond will tell us what kind of bond will form between them. A polar covalent bond will occur if the two atoms participating in the bond have an electronegativity difference of somewhere between 0.4 and 1.8, as this is a difference that will allow for electrons to be shared, but unevenly between the atoms. If the electronegativity difference is larger than 1.8, the electrons will no longer be shared. One atom will steal electrons from the other, and an ionic bond will form. If the difference is less than 0.4, we say that the bond is essentially nonpolar, or pure covalent, where the electrons are shared roughly evenly between the atoms. Another way of stating this is saying that as the electronegativity difference increases, the ionic character of the bond increases from pure covalent to polar covalent to ionic, or from electrons shared completely evenly to being shared unevenly to not being shared at all. To find out what kind of bond will form between two elements, just consult the table of electronegativity values and calculate the difference.
We should now understand what ionic bonds and covalent bonds are, and how to predict the type of bond that will form between two particular elements. Professor Dave for Chegg. See you next time.